In this video, I'm going to show you how to estimate heterogeneous effects from experimental data. I have created an artificial data set, and I know the truth about the parameters of this data. I created 4 independent variables, x1, x2, x3, and x4. x1 is a Bernoulli random variable with probability of success equal to 0.5. x2 is a normally distributed random variable with mean 0 and standard deviation 1. x3 is Bernoulli, but with a probability of success of 0.6. x4, again, is a standard normal random variable. With these 4 variables, I'm going to create first the treatment variable. And notice, this is going to be experimental data. So the treatment is going to be independent of all variables. So the treatment is going to be Bernoulli, it's going to be 0, 1, with a probability equals to 0.3. So they're going to be about 30% of the observations are going to be in the treatment group, and 70% of the observations are going to be in the control group. Once we create the treatment variable, we can create the outcome variable, y. So y is going to be a function, a direct function of x1 and x2. And notice it's going to be also a function of t, the treatment. But there's something new here. Typically, we assume that t has a constant coefficient. But now the coefficient of t is a function of x3 and x4. That's what we mean by heterogeneous effect. The effect of t on y will depend on the value of some of the variables for a given observation. The higher x3, the higher x4, the greater the effect of going from 0 to 1 in t. There's a random disturbance at the end, epsilon, which is also normally distributed with mean 0 and standard deviation 1. I have created this data set. I have created 50,000 observations using this Python script. If you're interested in reproducing what I did, I could send you the script. Okay, so let's switch to Tableau. And what I want to do in this exercise is what I typically ask you during class. And typically the first question I ask is, you don't know that the data was generated as an experiment. So the first thing you want to do is you want to check, do I believe the claim that this data comes from an experiment, or I have serious doubts that this data has been generated by a random experiment. Okay, so I have all the variables here. And remember, the way we check graphically whether this is an experiment or this is an observational study is by comparing the distribution of all the x's across the 2 treatments. So here I have x1. x1 is binary, so I'm gonna convert this to dimension. That means I'm gonna convert it to a categorical variable. x3 is also binary, so I'm gonna convert it to a dimension. That's a categorical variable, a binary variable. And x2 and x4 are continuous. T is the treatment. 1 if the person receives the treatment, 0 if the person stays in the control group. That is also a categorical variable. Okay, so what are the things that I want to check? I want to check, let's see, what's the distribution of x1? So I'll select x1 and number of observations, and then I'm going to do a bar graph. Okay, I prefer vertical bars. So this is the distribution of x1 for all the data. People in the control group, people in the treatment group. And what I want to do is I want to compare across the treatment. So what I'm going to do is I'm going to put this here. And they should have the same distribution. Remember here, 70% of the data are in the control group and 30% are in the treatment group. So the graphs are not comparable. So I have to do something else here. I have to say, show me the graph as a percentage of the row. So now you're going to see percentages here. 50% 1, 49% 0. And here is slightly bigger, 51, 49, but it's not a big difference. So we say, okay, looks like they have the same distribution when t is equal to 0, when t is equal to 1. Let's check the other binary variable, which was x3. So I'm going to put it here. And again, the same. They have the same distribution, 60%, 60%, but 60%, 40%, 60%, 40%. So they have about the same distribution. So the binary variables seem to be distributed about the same for the two treatments. Let's check the other ones, the continuous variables. And the trick here is you take a continuous variable and then you create a histogram. Remember, it was normally distributed. So here's the normal distribution. And what I want to do is I want to change the bins. So we're going to edit here x2 bin. x2 bin is created automatically when you create a histogram. Okay. So I'm going to edit here and I'm going to say the size of the bins should be 1. Okay. Okay. So here's the new histogram with bins that are not as narrow. Okay. One more thing to do here. You have to convert to discrete. If you don't do this, you're not going to be able to do the graphs that I'll do later. Okay. I'm going to do the same for x4. x4, I want to do a, notice there is no x4 bin here. It's going to be created when I create the histogram. Okay, so now I have x4 here, and I'm going to edit x4, and then I'm going to do the same. The size of the bins is going to be 1. And what else? And then I'm going to make it discrete. If I make it discrete, it's going to allow me to treat this variable as if it were a categorical variable. So I can come back here, and then I can say, I can take x2 bin, and then I'm going to put it here. Okay, so in the upper panel, we have the distribution of x2 when t is equal to 0. And it's about the same as when t is equal to 1. So the distribution of x2 is also the same across the two treatments. We can check x4 bin. Okay, and it's pretty much the same story. So graphically, we didn't see anything that questions the assumption that this data was generated by an experiment. Okay, how do we do that in Jamovi? Okay, how do I check whether this data was generated by an experiment? Okay, what we're going to do is we're going to run a binomial regression. We're going to try to explain how the observations were assigned to treatment 1 to treatment 0. Since they were assigned at random, I shouldn't do a good job at explaining t as a function of x1, x2, x3, and x4. Let's try. Okay, x1 is a factor, is a 1, 0 variable. Put it here in factors. x2 is continuous, x3 is a factor, x4 continuous. And what we want to see here is we want to see p-values, huge p-values here. Okay, and 90, 58, 16, and this is a small p-value. Okay, so we say, whoops, this should be equal to a very small value, but just because the world is like that, random stuff happens, we get a p-value of less than 1%. Is that huge evidence against the assumption of a random experiment? Well, before we say it is, let's check what it means to move from x1 equal to 0 to x1 equals to 1. So you're going to go here to estimated marginal means, and you're going to say, we're going to put x1 here, and you're going to get a graph here, and see, there's no big difference. Okay, and let's take a look at the marginal means table. And let's see what happens when I move from x1 equals to 0 to x1 equals to 1. What happens to the probability being assigned to the treatment group. And it goes up 1%. So it's no big deal. Okay, so yes, I didn't like the p-value that small, but it doesn't make a big difference practically. Okay, so we conclude that it looks like the data came from an experiment. Okay, second, we want to establish whether the experiment worked. Okay, whether the treatment works. How do we do that? We get the distribution of y. First, we're going to do it in Tableau, and then we're going to move to Jamovi. Okay, y. Let's do a graph, a bar graph. The default is sum, but I want to switch to average, to the mean. Okay, let's make it vertical. So the mean for all observations for y is 0.67. Okay, does it change the mean depending on the experiment, depending on the treatment? Let's put color in treatment. When I go to the blue bar to the orange bar, do I get an increase in y? And yes, I do. It's huge, the increase. I go from a mean of 0.24 to a mean of 166. So this is a change of about 140. Okay? We cannot make statistical statements here. We're going to do that after looking at the regression in Jamovi. But this is the graph that goes with the following regression. Okay, let's go here and let's run the regression of y, the dependent variable, the outcome variable, and the independent variable is going to be t. Okay, so see, the p-value of the treatment is equal to 0.0000, so it's statistically significant at any significance level. And our estimate of the change in the means is 141. Remember, that's what we saw in the graph. Okay, when I move from here to here, I'm increasing the mean of y in 141. The difference is that now I can make a statistical claim. Okay, I can say I could get a confidence interval. I can say a 95 confidence interval for the slope of t goes from 139 to 144. We have 50,000 observations, so we are very sure that this effect is different from zero, that is greater than zero. Okay? Now, this is an experiment, so this is it, right? We don't have to add controls to this regression. We could and we will, but we don't have to do it. All we want to do is estimate the average treatment effect. The average treatment effect is 141 here. Okay? Now, the next question is this increase in y as a consequence of going from t equals to 0 to t equals to 1 is uniform across different values for all the independent variables? This is a different way of asking. Do we think that we are in the presence of heterogeneous treatment effects? We're going to take a look at that graphically first, and then we're going to go back to Jamovi. Okay? Okay, so what does it mean to have heterogeneous treatment effects? It means that this increase from 0.24 to 166, which is about 141, if it is different for different values of any of the x's, then we have a heterogeneous treatment effect. Okay? So let's try. X1 was a binary variable. Okay? So let's put it here. And let's take a look at it. Is there evidence of heterogeneous effects? Stop the video and answer the question. Okay, what we're checking is what happens when I move from the blue bar to the orange one. What's the increase? So I go from 0 to 143. So it's about 140. Okay, what happens when x1 is equal to 1? When x1 is equal to 1, I go from 0.50 to 190. That's an increase in 140. So there doesn't seem to be any heterogeneous treatment effect here, at least with respect to x1. Okay, let's try the other binary variable, which is x3. Okay, let's try. Let's replace x1 by x3. And let's see what happens here. In this case, I go from 0.25 to 0.75, let's say. That's an increase in 0.5. That's when x3 is equal to 0. And when x3 is equal to 1, I go from 0.25 to 2.25. So here I have an increase of 2. Here I have an increase of 0.5. So at least with respect to x3, it looks like there is a strong heterogeneous effect here. Okay, the effect of going from 0 to 1 in t is going to be bigger if x3 is equal to 1. Okay, okay, let's try the continuous variables. Okay, what about x2? Okay, x2, let's put it here. And then we're comparing what happens when I go to the blue one to the orange one. I go from 238 to 0.62. So it's the distance that I'm comparing. Is that about the same distance when I go from 156 to 0.27? Yes, about the same. From minus 84 to 0.58, I'll get a calculator and get the changes from the blue bar to the orange bar. And you're going to conclude that they're about the same. The only place where it looks that it's different is at the end. Here we go from 240 to 457. But remember that we have very little data in that region, right? So we're talking about this region. Okay? Sorry. This is x3 in this region. See, we don't have any data here. So don't worry about it. Okay? So it doesn't look like x2, it doesn't look like we have a heterogeneous treatment effect, at least with respect to x2. With x1, I mean, with x3, there was, let's try x4 now, x4. And here, let's see, blue, I go from positive to negative. So there's a reduction in y. When I go from t equals to 0 to t equals to 1. The same here. T equals to 0, t equals to 1. Here, they stay about the same. Here, it increases. When I go from t equals to 0 to t equals to 1, y goes up. So see, we get changes in different signs here. So that's evidence of a heterogeneous effect. Look, here, they're pretty much the same. 0.24, 0.31. Look here. I go from 0.25 to 119. It's a big change. Bigger. From here to here. From here to here. From here to here. It seems that the effect is getting bigger and bigger as I move to the right. Okay? So it looks like I have a heterogeneous effect with respect to x3 and x4, but not with respect to x1 and x2. And let's go back to how I created the data set. Right? Remember, the effect of going from t equals to 0 to t equals to 1, see, depends on the values of x3 and x4. So there is heterogeneity with respect to those two variables, but not with respect to x1 and x2. So we're going to go back to Jamovi, and we're going to try to measure this heterogeneous effect with respect to x3 and x4. Okay, let's come here, and now we're going to include all the variables. The factors go in factors. The continuous variables go in covariates, x3, x4. If I ask you at this point, take a look at this regression, tell me, do you think, based on this regression, that there are heterogeneous effects? The answer is no. We measure heterogeneous effects, including interactions between the treatment variable and the variables, the independent variables we suspect there is a heterogeneous effect. Okay, we're not going to try them all. That's a very bad practice, including the interactions of all the variables. Okay, and I'm going to talk about this during the last week of the course. So we're going to try the ones we suspect. Okay, so we're going to say, I want the interaction between, what was it? x3 and t included, and between x4 and x3. Okay, And we have interactions, we have heterogeneous effects when the p-values of the interactions are small. Okay, in this case, they are very small. So we have evidence here that there is a heterogeneous effect. Now, careful here. So we have two variables here that have p-values. They're huge p-values. We might be tempted to get rid of them, but we cannot get rid of them when they're being used in interaction. See, x3 and x4, which don't have any, which have p-values very large, are used here, x3, x4. So we cannot get rid of them here, okay? And this looks like the final model, okay? And notice one thing. Did we recover the true parameters? Compare these coefficients with the coefficients that were used to generate the data. 0.5 times x1, 0.8 times x2, and then 0.5 plus 1.5 times x3, 1 times x4, multiplied by t. So the heterogeneous effect is with respect to x3 and x4. Let's check. And again, we get 0.5, 1.5, and then we get 1. See? And the coefficients of x1 and x2 are 0.49, about 0.5, and 0.8. Okay? And the fact that these numbers are very small is consistent with they were not present in the original regression, the original equation that generated this data set. Okay? I hope this helps you understand better the concept of heterogeneous treatment effects and how to estimate and how to detect them in experimental data. Okay?